Drones are everywhere today, shooting movies, inspecting wind turbines, and delivering packages. But if you look closely at how a quadcopter is built, its physical design presents a mechanical problem that should make flight impossible. Look at this 3D wireframe. To operate freely in three-dimensional space, any aircraft must move along 6 specific degrees of freedom. It has to shift up, down, left, right, forward, and backward, and it has to rotate along its roll, pitch, and yaw axes. But check the hardware. A standard quadcopter possesses exactly 4 inputs to achieve all of that motion. Those inputs are simply the variable speeds of its 4 spinning propellers. Engineers call this mathematical deficit under-actuation. The vehicle physically lacks the independent controls necessary for every single direction it needs to travel. 6 degrees of freedom, but only 4 ways to influence them. With parts literally missing from the mathematical equation, a quadcopter shouldn't be able to dart through the air with the agility we see every day. This severe hardware limitation forces a reliance on an invisible brain to keep the machine in the sky. Because of this under-actuated design, a drone cannot simply slide left or right on command. If you push a control stick sideways, the quadcopter has no lateral thruster to push it in that direction. To move sideways, the drone must intentionally unbalance itself. By speeding up propellers on one side and slowing the opposite, the entire airframe tilts. This redirects upward thrust into horizontal movement, forcing the machine into a controlled fall to travel from point A to point B. Managing that chaotic balancing act requires constant, microsecond adjustments to thrust. A human pilot with a joystick simply lacks the reflexes to independently control 4 separate motor speeds fast enough to prevent a crash. The onboard autopilot handles this immense workload. It acts as an essential layer of translation software, converting basic directional commands from a pilot into thousands of high-speed mechanical adjustments every second. Writing the complex algorithms that run this autopilot involves a massive amount of trial and error to get the math exactly right. The traditional aerospace development pipeline follows a strict sequence. Engineers draft control code on a computer, upload it to a physical prototype, and haul it out to a field for live testing. But out there, the physical world is unforgiving. Real testing introduces unpredictable wind aerodynamics and messy sensor noise. Out in the field, a single flaw in the algorithm guarantees an expensive crash. Discovering coding errors late in the physical testing phase triggers massive project delays. The entire engineering team has to halt their work, analyze the wreckage, and rebuild shattered prototypes from scratch. Relying on real-world hardware to perfect intricate autopilot algorithms is a broken system. It takes too much time, burns through budgets, and is far too dangerous to keep up with the rapid pace of modern aviation. To solve this bottleneck, the aerospace industry adopted a digital strategy known as model-based design. Instead of risking physical hardware, model-based design takes the entire testing and validation phase out of the real world and moves it entirely into mathematical simulation. It starts on a digital blueprint canvas. Engineers construct highly accurate digital models of the drone's physical parts. They simulate the exact weight of the airframe, the voltage drain of the battery, and the specific aerodynamics of the spinning rotors. Once the machine is built digitally, a virtual 3D environment is constructed around it. The simulation bombards the model with severe wind turbulence and injects artificial sensor failures, like dropping the GPS signal. This line graph maps the raw autopilot algorithms reacting to those stresses. At first, the system fails and crashes repeatedly, represented by these chaotic drops to 0. But because it happens in a completely safe digital space, the software can fail thousands of times, learning and refining until the flight path smooths into a perfect, stable wave. Engineers call this shifting left. By moving the destructive trial and error process to the earliest possible stage of software development, they isolate and fix critical logic flaws before a single piece of aluminum or plastic is ever manufactured. The final transition from the virtual realm to physical hardware happens seamlessly. Once the digital drone navigates its simulation flawlessly, the software automatically translates the model into the final embedded code. This auto-generated code is loaded directly onto the physical quadcopter's microchip. Bypassing manual programming entirely eliminates the risk of human typographical errors slipping into the flight systems. A rigorous formal verification process accompanies the software upload, mathematically proving that the generated code complies with strict aviation safety regulations. When that physical drone is finally taken outside for its very first real-world flight, it performs precisely as it did in the digital simulation. The incredible agility and safety of modern drones is the direct result of model-based design, solving complex mechanical paradoxes across millions of invisible virtual lifetimes.